This is Stockholm, the crucial link in a frightening story. In the Swedish Ministry of Defense, a scientist is discussing plans for an atom bomb. This is Jan Prawitz. The plans on his desk are not Swedish, and they are not for a military bomb. They were sent from Boston by Nova researchers with one question: would this bomb work? If the answer was yes, it would mean that many people could make an atom bomb, because the design uses plutonium that could be stolen in any of the 25 countries now developing nuclear power. And it was thought up by a student.
Hey, Gary.
5 weeks before, Nova had asked this 20-year-old chemistry student at a famous university in Boston to attempt the design.
Okay, that's great. Okay, good. Thanks. Bye-bye.
The object was to test an idea proposed by Ted Taylor. Now a Washington consultant, he spent 7 years at Los Alamos designing nuclear weapons. These bombs, works of genius according to colleagues, still wait in military stockpiles. Taylor now recalls the official Pentagon attitude towards unofficial atom bombs 10 years ago.
Looking at what people were saying about the chances that another group of people might go nuclear, they were always thinking in terms of something like a dozen countries. And I asked myself, why does one always speak of a highly industrialized country? Is it really all that difficult, given somehow, let's say, some stolen plutonium or highly enriched uranium?
Steal the material, make an atom bomb, and you'd have a blackmail weapon no government could afford to ignore.
In thinking about it myself, it was clear that it would be possible for a small group of people, possibly even one person working alone, to make what I would call a crude fission explosive.
But even in private, nobody seemed to be taking Ted Taylor seriously. So he started publishing his ideas. And along with the ideas had to go descriptions of how it would be possible.
In Ted Taylor's books, he cites a lot of different source materials and reference books that would be helpful in a person designing a bomb. Now, a lot of these references I ended up using, and they were helpful to me both for specific technical information and for a sort of general background. It wasn't indispensable that I had his book. I could have done without it, I'm sure, but he saved me some time. It was all gathered together essentially in one source, so it was a time-saving device.
This is not some secret government project that's going to last for a few years. It's going off in some corner somewhere. We're talking about what many people believe is likely to be the main source of power worldwide within something like 30 years. The public, I think, has the right to know what the risks are. It certainly has as much right as any prospective criminal might have to go to his local librarian and ask that person to do a literature search on what's available in the literature on how to make a bomb.
And that's almost how the student started. He simply went along to his college science library and started looking for the key references himself. They're not difficult to find. Under the conditions imposed on this test, the student had to work alone, without seeking any expert assistance. But buried in the stacks of any good science library in the country, and probably in the world, is a vast amount of information needed for designing a bomb.
Hi.
Hi.
He had to work fast. The film production schedule dictated a time limit of 5 weeks. It was a situation which recalled the wartime Manhattan Project and the race between Germany and the Allies to develop the first bomb.
Thanks.
But there was one obvious difference. In 1943, the scientists assembling at Los Alamos under strict security weren't sure if atom bombs were even possible.
the time the scientists all got together at Los Alamos, there was a lot they knew. They knew what nuclear fission was. A neutron strikes an atom. The atom splits. When it does this, this gives off radiation and energy and also gives off more neutrons. It's going to give off either 2 or 3. They also knew what materials could undergo this process. There's uranium-235, which is a component of natural uranium, which you mine out of the ground like gold. And there's also plutonium, which is a man-made element. They also knew about the possibility of a chain reaction. You take uranium-235 or plutonium, bring it together. Here comes a neutron again. Strikes an atom. The atom splits, energy and radiation, and more neutrons. These neutrons in turn strike more atoms, more energy and radiation, and more neutrons. And this process continues. Now, if it happens fast enough, if enough fissions occur, you have a bomb. And to give you an idea about how much energy and radiation is given off by this process, if you had 1.5 ounces of plutonium and it underwent complete fission, this would give you the equivalent energy of 1,000 tons of TNT. But there was a lot they didn't know. They had a good idea, but they didn't know exactly how much material they'd have to use. They also didn't know how fast you'd have to bring it together to get a bomb, and they didn't know any idea, they didn't have an idea about how to bring the material together.
This is Los Alamos today. In the center of one laboratory are 3 pieces of plutonium now being prepared for a critical mass experiment. Brought together, the pieces will be just under critical, almost enough for a chain reaction. Closed-circuit monitoring will be needed to avoid radiation. When the safety supports are removed, the experiment will be ready. Now the scientists have to leave. The control room is over a mile away. Safety precautions have been extreme since 1946, when one scientist died from radiation exposure after the plutonium sections accidentally fell together. A master control room feeds power back to the critical mass building. Now the pieces can be brought together. A meter shows that just a few neutrons are being produced. Just a few plutonium atoms splitting. No chain reaction yet. So a thin plutonium rod is run in from the left. Still no chain reaction. Now the ball of plutonium is just going critical. The neutron count begins to rise as more and more atoms split, slowly starting the chain reaction. But this could never be a bomb. Energy released by a strong chain reaction would blow the lightly held pieces apart instantly. So during the war, the scientists had to develop a system of explosives to force the critical mass together. In July 1945, a site at Alamogordo in the New Mexico desert was prepared for the first full-scale test. After 2 years' work, the exact condition needed to achieve a strong chain reaction had been worked out. The bomb was assembled in a tent under the test tower, then winched to the top. 30 years later, where are the results of all the Manhattan Project work?
These books contain information that was generated in the Manhattan Project. Altogether, they contain very much the basic science about how A-bombs work. There's a lot of technical information, hard information that's useful, and other things. For instance, this book is a technical history of the Manhattan Project. It was written in 46 and 47 and finally declassified in 1961. This is a good hard technical source. It's on critical mass data, and it was also written around that time, declassified in 1964. This is a good book. This is one of my favorite books. It's the Los Alamos Primer. It was used to orient scientists who were new to the project about the basic theories and the fundamentals of bomb design, and it is really good for an overview about the theory of bomb design. All these books are available from the National Technical Information Service in Washington, D.C. I went down and picked them up myself, about $5 a book, and the reference numbers, which I needed, I got from one of Ted Taylor's books, so it's really no problem to go down there and get enough information to design a bomb.
As everybody knows, the information is correct.
I was pretty surprised about how easy it is to design a bomb. When I was working on my design, I kept thinking there's got to be more to it than this, but actually there isn't too much to it. In fact, the design I came up with is a lot like the one they first tested, the bomb they first tested at Alamogordo. You have a central core of plutonium. It's about the size of an orange, or a little bigger than that, which is surrounded by an iron tamper. Now, the function of the iron tamper is to reflect neutrons back into the plutonium core so more fissions take place. Now, around the tamper is another shell of TNT. Those are circles. And the information I actually needed, the hard data for how big the plutonium core should be and how much TNT I need to use, I got from Los Alamos reference books and also other reference books I checked out of the library. Now what you do, you detonate the TNT, that squeezes the tamper and the core together enough that the plutonium becomes supercritical. It stays together long enough that you get a chain reaction and boom, you got a bomb. Really, it's that simple.
For 5 weeks, the student's room housed a miniature Manhattan project. In the final week, he wrote a complete report. There were sections on the scientific background of the design and full details on the sizes and weights of the parts. The figures here are covered to avoid providing a shortcut for anybody watching. The aim was to give enough information for the weapons experts in the Swedish Defense Ministry to assess the chances that a nuclear explosion would be produced if the bomb was built according to the students' instructions.
I think it's a very interesting report. It's a shocking report, even if there is a fair chance that this bomb will not go off. On the other hand, there is also a fair chance that it will go off. And then the yield, the explosion yield, would probably be rather low, less than a kiloton and probably less than 0.1 kilotons. Even if there is a very, very slight chance that it will produce an explosion yield above 1 kiloton.
A slight chance above 1,000 tons of TNT. A better chance less than 1,000 tons. More likely less than 100. Those are small nuclear explosions, but very large conventional ones.
The explosion of a ship which caught fire and blew up a dock at Texas City on Galveston Bay. Loaded with a cargo of fertilizing material, highly explosive ammonium nitrate, the vessel, a former Liberty ship now under the French flag, was blasted into shattered bits and hurled for miles. And that touched off a cataclysmic series of detonations.
Texas City, 1947. A ship exploded with a force equal to about 1,000 tons of TNT, equivalent to a small nuclear explosion.
The first work of rescue is under desperate conditions. The city cut off, communications down, the community utterly unprepared for calamity of such magnitude.
Here, casualties were low for the size of the blast. The main areas hit were docks, warehouses, and a refinery. But Ted Taylor has worked out what could happen in a busy city.
An explosion with a force of something like 100 tons of high explosive equivalent, which would be pretty well guaranteed even for a crude nuclear explosive, would be enough under many circumstances you can imagine to kill 50 or 100,000 people in a crowded urban area.
There was an outbreak of panic.
The student's bomb, if it was built, would inevitably be the most terrifying blackmail weapon ever devised.
I think that in the hands of a terrorist, from the point of view of the authorities negotiating with the terrorist, the fact that the bomb might go off is the important thing.
This could be New York, London, Belfast, Tel Aviv, any big city. It seems unthinkable that just 5 weeks of a student's time could come up with this potential. Why is the information he needed so freely available?
Unclassified reactor technology research has improved all the time, and that it is necessary to understand this, to publish a lot of things that is also essential for designing the bomb.
This greatest of destructive forces can be developed into a great boon for the benefit of all mankind. United States
1953, President Eisenhower at the United Nations. It was time to end the Cold War, he said. Take the bomb away from the soldiers and start exploiting the peaceful atom.
A special purpose would be to provide abundant electrical energy in the power-starved areas of the world. To hasten the day when fear of the atom will begin to disappear from the minds of people and the governments of the East and West, there are certain steps that can be taken now.
One of the first steps after Eisenhower's speech was the first Atoms for Peace Conference in Geneva, 1955. The United States showed an experimental reactor in public for the first time. To aid nuclear power development, America and Russia started a massive declassification program. But nobody imagined the information might be used in unofficial bomb designs 20 years later. To actually build a bomb, you'd need plutonium. And to find it, you'd have to understand the nuclear fuel cycle. Natural uranium ore is first refined to make power reactor fuel rods. It's impossible to make bombs with these. In this typical reactor, 100 tons of fuel rods have to be loaded into the core before a slow chain reaction will even begin. While the heat from the reactor goes to make steam for the power station, some of the uranium inside the fuel rods is converted into plutonium, and some into highly radioactive waste products. Every few months, reactor engineers have to load up heavily shielded shipping casks with what they call spent fuel. Bundles of radioactive fuel rods are maneuvered into the casks under a water radiation shield 20 feet deep. It's a process now happening worldwide. This is an Italian spent fuel shipment on its way to Windscale on the deserted fringes of the English Lake District. In what's known as a reprocessing plant, the fuel is cut up into small sections at the start of a complex chemical process designed to extract plutonium from radioactive wastes. The plutonium first produced here, as in America, was used for military weapons. But now, a major new use of plutonium is planned. A development at this reactor on Lake Michigan was observed by Roger Connor, a local environmentalist, with great interest.
That's the Big Rock nuclear plant. It was one of the first nuclear power plants to start producing electricity in this country. And it's been involved in the last few years in a very important technology development program by the Atomic Energy Commission. What they've been doing is placing small quantities of plutonium in the reactor on a regular basis, using it as a fuel and experimenting with it in different ways. Well, in December of 1972, the Atomic Energy Commission told Consumers Power Company that they could place a full core reload of fuel containing plutonium in that reactor. Now, this was a very important step. It was the end of the research program, the beginning of commercial implementation. And indeed, Nuclear Technology, which is the magazine of the nuclear industry, called this a milestone in the history of nuclear power.
Roger Connor agreed. Applied throughout the industry, it would mean widespread manufacture, storage, and transport of bomb material. He wanted an environmental impact study.
So what we did, we sent the Atomic Energy Commission a telegram. In that telegram, we demanded simply that the Atomic Energy Commission and Consumers Power comply with the law. We filed a lawsuit shortly after we sent that telegram when we got no response, and there have been court proceedings and administrative proceedings since then. But in sum, what's happened over the last year and a half is this. The Atomic Energy Commission has conceded that they do have to file what's called a generic environmental impact statement, evaluating this program and giving it a systematic analysis.
The draft statement came out last year. In theory, plutonium reactor fuel cannot be used before a final statement is approved. But in practice, things look different. Here in South Carolina, Allied Chemical, Gulf Oil, and Royal Dutch Shell are investing $500 million in a plant for extracting plutonium from spent fuel, as in Windscale. Gary Molan will be in charge of keeping track of plutonium when production starts next year. Does building the plant mean that plutonium recycling will in fact go ahead?
I'd have to say I think it's unlikely that a reprocessing plant would be built if, in fact, plutonium was not intended to be reused, at least at some point in time.
It's an attitude held throughout the industry. As a fuel, plutonium is worth $5,000 a pound. As waste, nothing. Up to 70 pounds of fuel a day will be going into the storage tanks at Allied General. Enough for nearly 2,000 homemade bombs a year. With widespread plutonium use, a virtual certainty in the future, what does the Atomic Energy Commission think about the possibility of people making their own bombs? General Giller is in charge of material security.
They'll be in the position probably of not knowing whether that thing will explode, and so will you. But since there is the possibility, in your case, being on the receiving end of a threat, you have to assume that it would be possible. Therefore, it's obvious that you put your effort on preventing the loss of the material. Let's keep the horse in the barn rather than look for it after it's been taken.
This was one of the first of General Giller's barns to be set up. Run by Kerr McGee, an Oklahoma oil company, it's a factory making experimental plutonium fuel. And this is the horse, a can of plutonium oxide. 2 cans contain about the right amount for one crude atom bomb. Anywhere plutonium is handled, bomb making is not the first concern, it's safety. The type of radiation it gives off can be stopped with a rubber glove. But if a single plutonium dust particle is caught in the lungs, that same radiation will cause cancer. So all processing is done inside sealed glove boxes. But because only 2 of these cans would be needed for a bomb, the company has to try to keep track of all the plutonium moving through the process. Measurements are made and continuous records kept. It's a process known as inventory control, well known in any industry where valuable items are handled. The question is always the same. How accurate is it possible to be? It was applied to nuclear materials 20 years ago during the Manhattan Project. At Oak Ridge, Tennessee, some of the first bomb material was processed. Dr. John Guggen explains how good the control has to be.
In the safeguard sense, we would like to be able to measure things, control things well enough so that we're sure nobody has taken enough material to make an explosive critical mass. Back in the days when we only had a few critical masses, that was very easy. In the days coming when we're going to have thousands and thousands of critical masses, that is going to be extremely difficult and is really beyond the ability of inventory control to measure.
This is a can of plutonium fuel pellets leaving the process at Kerr McGee. A routine measurement will be performed and checked, but it's not good enough.
There are limits to how accurate you can measure things.
Can 88.
And 88.
White. 1,477 grams.
If you're using balances, then there are limits to the accuracy of the weights and the corrections and the things like absorption of moisture on your materials make it most difficult to weigh.
But they have to do the best they can. The stakes are too high, and the difficulties don't end with simple weight measurements. This worker's got a contaminated glove. A counter tells him to get rid of it. But along with the glove goes a trace of plutonium. Bags of waste are generated all the time, so the plutonium must be counted.
If you're doing radiological counting, then the statistics of the counting system are a finite limit. The longer you count, the better, but you can't count forever. And all of this data has to be put together to balance, to try to balance how much you have versus how much you have put in and taken out and still have, to get a balanced system so that you can tell where things are and what's happened to them.
Every 2 months, they're required to produce a full inventory of the plutonium they've handled. Now all those measurement inaccuracies have to be combined into an overall error. It's shown by the letters LE, limit of error, on the inventory. The result is a MUF, material unaccounted for. Filming the actual figures was not permitted, but a MUF of at least 1% of the total quantity of processed plutonium is unavoidable.
1% of inventory in a plant of the present is barely good enough. In a plant of the future, where there are much larger amounts of material, you have lost several critical masses in a month, and in that time, a skillful person can have his project finished. So that a % accuracy in a month or two's time is just not good enough.
At Kerr-McGee, 1% every 2 months means about 2 pounds missing. In a year, 12 pounds, about enough for one bomb, undetectably gone. But throughout the industry, there's going to be a further problem. John Guggen explains.
Somebody might be removing material in a very subtle way and want to take perhaps months or years to do it. Therefore, you have to have, on a longer time scale, very accurate measurements of what is going on so that you can detect the small diversion on a continuing basis. And of course, this is the one which is the most difficult to detect and is most easily covered up by a skillful operator. An instrument technician could, in fact, alter the instruments themselves so that they report uniformly the wrong answer. So, to given very sophisticated people in the system, they can cause almost complete havoc if they really so desire.
At Los Alamos, possible havoc in the industry seems remote. But the measurement problem has concerned one scientist who lives here, Bob Keepin.
This jungle of pipes and tanks and vats and valves does not lend itself to easy measurement because it's quite a hodgepodge. Might say also that fissionable materials can be in different chemical forms, oxide, nitrates, carbides. They can be in different physical forms, in lumps and chunks, mixed in with sand or floor sweepings, or there is a category that's technically known as GKW. That stands for God knows what. And it has to do with just the unknown matrix in which material can be found. You've got everything from rubber gloves to Kim wipes and, as I said, sweepings. And so this just adds to the problem of measurement.
This is a sealed can of industrial plutonium waste, maybe even GKW, received by Keepin's research group at Los Alamos. They're using an experimental machine to measure very accurately the plutonium content. The factory measurement claims there are 122 grams of plutonium inside. Keepin aims to develop a range of machines linked to a central computer which could keep accurate accounts of nuclear materials throughout a factory. The result of the analysis, 162 grams. The factory was 30% wrong. Could a computerized system be the answer?
Now, in fact, the computer can be a hazard because sometimes you really forget what it's telling you and how it's programmed, and somebody who does know on your crew that how it's programmed can make it lie to you very easily.
Your system can only be as good as the people that you have working it. If in fact you are not able to employ trustworthy people, then you can design no system, no physical material system which can override them, because there's always some way to work around it. No system in itself is absolute.
While inventory control might never be able to detect theft from inside the plant, simply breaking in is the most obvious way for a bomb maker to get his plutonium. At Kerr-McGee, they've got all the guards, fences, and alarms that the Atomic Energy Commission now requires. There's a metal detector for guns. And an explosives detector inside. The objective of any break-in would be the vault. It contains over 400 pounds of plutonium at a time. The whole system is designed to keep out maybe one or two thieves. But what size attack should they expect? This is Belfast. Political terrorists work in large, organized, well-armed groups. The Middle East. Terrorists like to use bombs. They aim to disrupt. They don't mind who gets in the way.
How was it out there? Well, it was rough. It was rough. That's about all I can say. Stay over there. Stay on this side of the street.
The SLA in Los Angeles. Dozens of police were needed to hold down just 6 opponents.
Come out of the house and you will not be in the house is on fire, man. What are you talking about smoking here?
Anywhere a terrorist group has chosen to operate, the Munich Olympics, for instance, tremendous opposing forces have had to be brought in. They're not the slightest bit disturbed by casualties. And at Munich, they penetrated with ease a conventional security screen enclosing the Olympic Village. They are a new force to appear in the world. And their appearance was noted with alarm back at Oak Ridge, Tennessee, where Bill Sargent is director of security.
This old guard tower brings back some interesting memories. It wasn't actually fixed in the ground. We might even recall it to active duty. Now, it wasn't here during World War II, because in World War II we were concerned about espionage. So our physical security program was designed to prevent the loss of information, not to repel some attacker or invader. But following World War II, when the world knew that we had a nuclear weapon, we foresaw the possibility that someone would try to sabotage our plants. The protection had to be against some attacker from a foreign power. And that's why we had this kind of structure. It has bulletproof glass, steel plate through which the guard could fire. There's even an amount here in which we could place a machine gun. The structure is reinforced concrete. It had a searchlight on the roof. It could be turned by the guard. This is really the kind of thing that we are thinking about again today. we have seen that terrorists are willing to do almost anything to accomplish their objectives. So today we are concerned, in a sense, as we were 25 years ago, with someone who might try to invade, attack our facilities, and steal, divert special nuclear materials for some evil purpose, that purpose to influence events to suit themselves.
Commence fire!
Would Bill Sargent's guards, armed with pistols, be enough to stop a terrorist attack on this government weapons factory? He's done as much as his budget will allow to strengthen the defenses, but it hasn't been much.
We've taken steps to enhance the protection of this room in light of the increased threat. This is a very important room. We call it our Security Operations Center. It possesses security communications facilities with all of the security elements and all of the law enforcement elements in this area. Some of the things we've done is to install bulletproof glass in the room, put heavy steel plate on the door. We've also put television monitors to assist the officer in his controls from this point.
It might not be enough to stop a strong attack. What else would he like to do?
I'd like to see some additional guards at our plants, and I'd like to see them assisted by some of our most sophisticated alarms that are available today that would give them a chance to be forewarned of any attack on them. I would also like to see the guards equipped with the latest type of military ordnance. I'd like to see them have available some kind of hardened facility protection along the lines of the old guard towers that would enhance their ability to combat any people who are trying to enter the plant illegally to divert special nuclear material.
If the defenses are not adequate at this government factory, what are they like in the civilian power industry? Security at the new Allied General Plutonium plant is described by Gary Mullen.
We are not in a position to, nor do we plan to be in a position to actually prevent or try to stop a significant armed attack. It's not in the requirements now, and private industry is not in a position where they're willing to take on that responsibility.
Gary Mullen defined a significant armed attack as anything above 2 or 3 people. What size attack would the Atomic Energy Commission expect?
One feels that something in the order of 10 to 12 actual attackers is probably the maximum threat that would be credible in the U.S.
The systems that we design would probably not prevent them from entering. We would certainly deter them, we would detect them. And we have the communication systems available to us as part of our overall security system, which would enable us to call for reinforcements.
Security here will depend on reinforcement, but only 4 policemen are stationed nearby, and when asked, South Carolina State Police revealed they would need 45 minutes to assemble a large force. Kerr-McGee's plutonium fuel factory depends on the same reinforcement system. A maximum of 13 police are within 10 minutes. Large-scale reinforcements, 50 minutes. Does General Giller think the situation is satisfactory?
What remains to be done yet is to increase the amount of physical security that we perhaps employ in what we call fixed sites, a manufacturing plant, or in the weapons case, perhaps one of our assembly plants, where there it would be a question perhaps of more of the same, more guards, maybe sort of armored vehicles would be made available to them that we don't have at the moment. And this will take us into the years ahead in a way that is a little hard to foresee now.
So plutonium at fixed sites might not be secure against terrorist attack, and plutonium inside the factory cannot yet be accurately accounted for.
Oh!
And what about the plutonium that has to be transported? This shipment is traveling in the approved AEC manner by commercial armored car, the same type that's used to carry money. There's enough plutonium in the drums for 2 or 3 bombs.
Okay, go.
The latest AEC regulations specify a chase car with 2 armed guards. Most civilian nuclear transport is arranged by one Washington shipping agent, Sam Edlow.
Well, I think there's no question, but that from the point of view of security, when nuclear materials are in the transportation cycle, they are most susceptible to diversion. You have 2 possibilities. Possibility of pilferage and the possibility of overt hijacking. Everybody in transportation agrees that pilferage is not the problem. It's overt hijacking.
4 armored cars carrying money were hijacked last year in the United States.
This is Washington Unit 95 calling that.
To give warning of a hijack, the AEC requires communication back to base every 2 hours.
Please place a collect call to area code 202-833-8237.
The system using conventional radio telephone is cumbersome and unreliable.
This is Dave. Go ahead.
This is Operation 105 reporting a 1020 of Charlie plus 15 miles.
10-4. Your next call will be due at
1430, 10-4.
Sometimes even the radio telephone can't be used.
95 clear.
I would say that I think anything that we can do to improve it, we need. The present system that they're using, we run into blackout areas due to terrain. It's basically a matter of terrain. On most of our runs, we have a few blackout areas where our vehicles must use landlines to be in touch with us on a regular scheduled basis.
Hijacked in a blackout area, it could be hours before the alarm went out. Nobody disputes the fact that nuclear transport is insecure. An eventual solution is now being worked out. Using first this truck designed originally for weapons shipment. It's supposed to be able to keep people from getting inside for several hours. Exactly how is secret. A second element is inside this camper. It contains a new communication system designed to work anywhere, anytime. Using a series of prearranged codes, you can send up to 100 messages. Picked up by one of 5 ground stations across the country, the message is relayed to a control center. Truck identification and position are sent automatically. It's the same as the fixed site theory. Delay the attack and call for reinforcements, if they're available.
I think it has yet to be seen to what extent the communication systems between the vehicles that are carrying these materials and law enforcement forces and perhaps military forces will be to see to it that if a theft is delayed, as these specially designed vehicles are designed to do, sufficient strength, armed strength, appears in time to keep the material from disappearing from view.
What does Ted Taylor think of the overall response since he first revealed his fears about homemade atom bombs?
As of today, I think we still have a quite significant distance to go in this country to protect the material so that we can be reasonably sure that a well-planned criminal effort to steal the material while it's being transported or at fixed sites is not successful.
And that, unfortunately, is good news for terrorists, because the plutonium security developed in the United States is probably the most advanced in the world.
If stealing plutonium is easier in one country than in another, the measures undertaken by the second country will be worthless, because the terrorists can go to the first country and steal the plutonium and threaten the second country anyway.
This is Vienna, the headquarters of the International Atomic Energy Agency, which now faces the incredible task of keeping track of the world's growing mountain of plutonium. They run a materials accounting system in the same way as the United States. Ted Taylor's estimate of over 100,000 pounds of plutonium accumulated worldwide by 1980 gives an idea of their difficulties. That's enough for 10,000 homemade bombs.
Emilio, den Zurugerfall, bitte.
They rely very much on materials accounts provided by individual countries. This one's from Japan. But there are often long time delays, and measurement errors and material unaccounted for are as unavoidable as in the United States. To back up the reports, the agency runs a series of inspections. This is a Swiss reactor being visited by an inspector to monitor fuel reloading. A country might be diverting its own spent fuel, reprocessing in secret, then making bombs with the plutonium. As the fuel bundles are removed from the reactor core, the inspector keeps count. It's large-scale national diversion that the agency hopes to detect. Catching a factory plutonium thief is still up to the individual country. Back in Vienna, the IAEA Inspector General, Dr. Romech, was asked what he would do if he did find a large-scale diversion.
When we have the proof, there is a foreseen way of giving the message further. I report to the Director General of this organization. He reports to the board. The board might order an additional investigation, or, if the case is crystal clear, would report to the Security Council of the United Nations.
So at least the world would know about it. But since it hasn't happened yet, nobody can say whether the Security Council could take any effective action. Agency membership and inspections come automatically with signature of the Nuclear Non-Proliferation Treaty. Most countries of the world have signed, but a few haven't. A Canadian reactor supplied with no effective restrictions provided India with the plutonium she exploded last year. This is the only photograph so far released, but the explosion may have looked like this: an American plowshare shot. The Indian government claims its explosion was for peaceful exploitation of mineral deposits. They could have bought the technology direct from the United States or Russia, but chose not to. The Israelis as well haven't signed the Non-Proliferation Treaty. Their plutonium is produced with a French-supplied reactor in the Negev desert. 8 other countries have not signed the treaty. Preventing national nuclear proliferation is now practically impossible. Should the agency instead turn its attention to worldwide plutonium security?
I think that an international agreement on physical security of fissionable material is essential for the future. Otherwise, one have to rethink about the whole nuclear power industry.
An attempt at agreement was made. This booklet of security advice was prepared by an agency committee. But agreement among members to even call it an IAEA publication could not be reached.
If you look at the overall situation of the world and the fact that the agency has 105 member states, the probability is not very high that there is such a degree of consensus between them that the agency has more than the character of a secretariat of these 105.
I think there's a very good chance that, certainly by the end of the century, nuclear violence, quite possibly not involving national military use of nuclear explosives, will have reached the stage that most of us would consider intolerable.
In most countries, People will think that if terrorists are going to get atomic bombs because of the grow up of the nuclear power industry, we would better scrap the power industry.
In the United States, reactor accidents are seen as the major potential danger of nuclear power. It's one reason industry opponents have demanded a shutdown.
50,000 dead. That's what could result from a serious accident at just one small nuclear power plant, according to an Atomic Energy Commission report. It all adds up to this. Nuclear power is a terrible way to go.
Now, plutonium and bombs is a new reason.
The more nuclear power plants we build, the more plutonium we'll have to worry about. An accident could be a disaster. God bless you, America.
The demand by society to see that atom bombs don't get into everybody's hands is going to be almost a hysterical demand. And the response to such hysterical demands that we must protect our lines of plutonium shipment, our factories, means that everyone involved in that entire chain must necessarily be subject to security evaluation and surveillance, because everyone is a possibility.
There's going to have to be extensive personnel security checks and classifications reminiscent of the 50s in our country. There's going to be private dossiers built up about people, filled with answers to questions such as what magazine have you read and who did you associate with that was considered radical or unstable.
And if you have the largest industry, the largest single industry in your land, subject to this sort of security, that means the largest fraction of the workers in your country are subject to this sort of security. And this means a garrison state.
A garrison state, possibly. What's certain is that the type of information now available to the public will have to be cut back. This is the AEC's public reading room in Washington. It's the first place a bomb designer would visit when he was planning his plutonium theft.
Hi. Can I have these files, please?
All right, be just a moment.
Okay, thanks.
On file and freely available are the plans of every civilian nuclear installation in the country.
Thanks. Put them all down, I guess.
If you need additional documents, you may add them to the bottom of the slip.
Okay, this will keep me busy for a while. Thank you.
Welcome.
These are the plans, for example, of Kerr McGee's plutonium fuel factory. You can examine the layout of the security fences and locate the plutonium plant. Inside the plant, you can find out where the vault is and the design of its door. Ralph Nader's attitude to the industry is clear.
It's technological insanity run amok. It's economic disaster. It's a vast invasion of privacy. It's the intrusion of the national security state into most areas of the country where people live. For what?
You're turning on more electricity than ever before. Your demand for electricity doubles every 10 years. Doubles.
At PSE&G, we're meeting the increasing energy demands of today and tomorrow with modern, dependable nuclear power plants.
Clean, reliable nuclear power.
A nuclear generating plant is as harmless as a chocolate factory.
But a lot more nuclear power is needed. Nuclear power. The power to keep America turning on.
If we, for example, decided for one reason or another to stop nuclear power development in this country, in the United States, the pressures that would continue in a country like Japan that has no indigenous sources of fossil fuels to continue whatever we do would continue to be very big. And I think it's really whistling in the wind to call for an international moratorium on all nuclear power development or a halt to all nuclear power development. I think it's just completely unrealistic. I don't think it will happen.
Which is why he raised the idea of simple atom bombs in the first place, and why some began to listen.
And I don't know if I'm influenced by the publicity that we've seen this past year. Perhaps I am. But I guess I would consider the nuclear blackmail threat perhaps a little bit more realistic, probable, than previously, when I stopped to think that nuclear power plant accidents have to do with the malfunctionings of machines, and let's face it, nuclear blackmail, clandestine weapon manufacture, and terrorism has to do with the malfunctioning of men.
I have great respect for the damage that can be done. Nuclear weapons, something I understand. And I don't want anybody to have one who's not knowledgeable himself of what he's going to be able to do. And who's not, no reckless person should have a nuclear weapon.
We've got a very few years to get this problem under international control. If we don't do much more than we're doing today, or are even planning to do today, within the next 5 or 6 years, I think there's a very good chance the problem will be permanently out of control. The reason for that is that there will have been so much material accumulated throughout the world that to try to put it under heavy safeguards at that point may be like trying to do a roundup of cattle that have left the barn and have gone out into the wilds and are essentially lost. In other words, there may have been material diverted or stolen before an effective system is set up, in which case it's gone.
It's a shocking report.
50 or 100,000 people.
Fair chance that it will go off.
Let's keep the horse in the barn.
GKW stands for God knows what.
Terrorists are willing to do almost anything.
10 to 12 actual attackers
will have reached the stage that most of us would consider intolerable.
We would better scrap the power industry.
Its technological insanity runs amok.
It may be the most difficult problem that's ever faced the world as a whole.
The material on this video cassette is protected by copyright. It is for private use only, and any other use, including copying, reproducing, or performance in public, in whole or in part, is prohibited by law.